Hello, students. Some of you are having problems with the ionic bonding gizmo, so here is a video walkthrough of that. So the first thing you're going to do is you're going to log on to Explore Learning Gizmos from your home page, okay? And you should be able to choose what class you want. I'm going to choose ChemCom because that's the class you should choose. And ionic bonds, I'm going to go ahead and launch that. Okay, so here it is. Like I told you before, I'm going to check this, and that. Now, if you go and get your gizmo open, remember it's in classwork under Thursday, 9:30. And go ahead and click that open. I have one open right here. I'll make this bigger so you can read it. And remember, ionic bonds are all about giving electrons away or taking them. There's no sharing. So the first two questions sort of get you in that mindset. With Nate and Clara, Nate has 9 markers, Clara has 7. What are they going to do? Nate will give Clara 1. Okay, here we go. Maggie has a table with Fred and Florence. Now we're adding a few people. Maggie has 10, and they each need 8. So instead of sharing 1, she's going to share 2. Maggie will give. Maggie will give her extra markers to Fred and Florence. All right, so now we're down to the gizmo. We're talking about valence or outer electrons, remember? It says each atom consists of a nucleus and shells. The outermost is the valence. How many valence electrons does sodium have? So we look. Sodium is the purple. We see 1. That is its valence electron. So the answer there is 1. And chlorine, let's look at that. 1, 2, 3, 4, 5, 6, 7. Chlorine has 7. Okay. Here it says metals do not hold on to their valence electrons and nonmetals hold on to them tightly. Meaning if you try to pull them away, it'll pull away from the metal, but it will not pull away from the nonmetal. So let's try that in our gizmo. We'll try the green one first. Down here you can see green means chlorine. I'm going to try and grab and pull. Nothing is happening. Now I'm going to grab and pull. Look at that. The sodium, purple is sodium. The sodium will pull away. And since metals do not hold on to their electrons, sodium did not hold on to its electrons. Sodium is the metal, making chlorine nonmetal. Now we're going to move it from sodium to chlorine. And look, it went over there. So what happens? It moves over to the chlorine. All right. So here we go. Activity A, click reset. Reset. Make sure sodium and chlorine are still checked. It says how many electrons are there total. So for this one, I'm going to unclick hide inner electrons and count them. Counting all of those purple dots, I count 11. Okay, sodium has 11. Chlorine, counting all of those dots, chlorine has 17. Now, based only on that, since they're neutral, they have to have the same number of positive and negative. So sodium has 11 protons and chlorine has 17 protons. They have to balance. So here we go. How many outer electrons does each have? Well, we answered this earlier, but let me show you again. I'm going to hide the inner ones now. We don't need those. 1 for sodium, and 7 for chlorine. Okay, that one, 7. Now I'm going to pull this over, and it shows me right there the charges, +1 and -1. So the next one, what are the charges? Sodium is a +1, chlorine is a -1. Okay. Is each ion stable? Explain. Let's check. If we check, it says, good job. All atoms are stable. Yes. And the reason for that is they now both have 8 valence electrons. Remember, 8 is that magic number that we're trying to get to. Why is there an attraction? Okay, so this is like how a magnet sticks to a fridge or other magnets. The positive end, the north pole of one magnet, sticks to the south pole of another. They're attracted because of that magnetic force. The same is true of ions. That's a positive and a negative. The positive and negative will stick together because opposites attract. So reset. And it says select lithium and oxygen. So we're going to reset. And from this drop-down menu, we're going to choose lithium and oxygen. All right. How many electrons will lithium give up? So that just means how many valence electrons does it have? Lithium is the purple. It has 1. How many electrons does oxygen need to become stable? Let's count. It has 1, 2, 3, 4, 5, 6. And 8 is the magic number. So 8 minus 6 will tell you how many it needs. That's right, it's 2. I wasn't trying to trick you. It really is that easy. So can a stable compound be made from these 2 atoms? Well, if we look at it, the math just isn't there. Lithium can only give up 1, but oxygen needs 2. So no. And I'm going to write that. Lithium gives 1 electron, but oxygen needs 2. All right. So now it says to add metal. So now we're not just working with the 2 atoms, but we're going to work with 3. Now we can give the electron from 1 lithium to oxygen. And if we check, still not stable. So we're going to pull this over. We gave oxygen its 2 electrons that it wanted, and we exposed the inner full shell of lithium. So yes, we did. For us. Edit, undo. Sorry about that. So what is the formula for this compound? Li2O. Show you where to find that right here. Show formula, Li2O. So what's the charge? Each lithium is a +1. And oxygen is a -2. If we look, right there, +1, +1, -2. So here we go. We're making chemical formulas. So lithium, we know is a +1. Reset. So lithium and fluorine. I'm going to drag it. I'm going to check. That one is finished. So +1, -1. The formula is Li. Now we're working with beryllium and oxygen. So we're going to reset, pull down beryllium, pull down oxygen. Now we can see beryllium has 2 to give. And if you remember, oxygen needs 2. So this should be an easy one to do as well. We're going to check. Yay. So we have a +2 and a -2 charge. And the formula, EeO. Magnesium and fluorine. We're just rolling today. Reset. Magnesium and fluorine. If we look, fluorine only needs 1, magnesium has 2. So we've run into this where we have this spare electron. It can't go over here. Fluorine doesn't want it. But what we can do in this case is we can add a nonmetal. That gives us another fluorine that wants another 1 electron. Pretty tricky, right? Let's see if we're right. Check. We are. So our magnesium right here has a, yep, 2+ charge, and fluorine has a 1- charge. Sometimes my brain just misfires on me. So we have a +2 and a -1. And we have MgF2. Now we're working with aluminum and chlorine. Reset. Aluminum and chlorine. And if you've been paying attention so far, you can see that we have another issue where one has more to give than the other can accept. Because we have 2, 4, 6, 7. Magic number is 8, so it wants one of aluminum's electrons. But now aluminum still has 2 it wants to give away. So what we have to do, and we'll check just so you can see, is we have to add another nonmetal. We have to add chlorine. And if we do that, we can give this electron away. We're still not there yet. So let's add another nonmetal and pull this last electron over and check. We did it. That one would have been very tricky to try on your own, I think. So we have aluminum with a 3+ charge. So 3+, and each chlorine has a -1. We have AlCl3. All right, last one, beryllium and nitrogen. Reset. Beryllium and nitrogen. All right, so let's see what the math is here. We have 1, 2, 3, 4, 5. It wants to get to 8, so it needs 3 more. This one has 2 to give away. So let's just keep plugging away at this. We know it wants both of these. Okay, but it's not happy yet because it still has this one open spot. This one has no more to give. This one doesn't want to give those 2 away. So we have to add another metal. Move this down, move this down. And we have to pull this electron away. Now this atom is happy, but this one is not. It still has an electron to give away. So let's add a nonmetal. This one gets really tricky. So we're going to pull this over. This one is now happy. These 2 are happy little beryllium, but this one still needs 2 if we check. So what we have to do is we have to add another beryllium to give electrons away. It's starting to pile up on us. Okay, pulling this one over. Now, does it have room for this last one? Let's check. It does. Let's see if we finally made a stable compound. We did. We have this 2+ charge and 3-. So let's put that +2, 3-. So that's Be3 we had to add, and 2. That one was tricky. If you did that on your own, give yourself a pat on the back. All right, so here we go. Lithium periodic table. Reset, lithium, and I think we can just drag that away. Yep. So we have lithium. Lithium has 1. Now look at your periodic table, find lithium. Other than lithium, which one is in the first column? I'll give that to you. It's sodium. If we choose sodium, as we've done a lot, you'll be able to see sodium also has 1. There's the pattern. And who doesn't love a good pattern? All right, so here we go. Beryllium and magnesium. We're going to look at beryllium first. It's this greenish one. It has 2. Now let's look at magnesium. Also 2. A pattern is emerging. Nitrogen and phosphorus. Nitrogen is already selected. 1, 2, 3, 4, 5. And if we check phosphorus, 1, 2, 3, 4, 5. All right. So we're going to put that in. 5 and 5. Oxygen and sulfur. Oxygen, 2, 4, 5, 6. Sulfur, 2, 4, 5, 6. And fluorine and chlorine. Let's take a look. Fluorine, 2, 4, 6, 7. And chlorine, 2, 4, 6, 7. What pattern do you see? Same group equals same number of valence electrons. So based on your data, how are they arranged? By valence electrons, that's right. All right, so periodic table. We don't have our periodic table out. Sorry, so I'm going to give these to you. Carbon has 4, boron is 3, and neon is 8. So how do you think the number of valence electrons relates to an element's chemical property? I'm going to give you that one too. Same number of valence electrons equals similar chemical properties. Perfect. So now we've done this together. If you needed answers and I moved too fast, this is a video. Rewind and pause where you need it. All right, get that done and turned in to me.